Ya, Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Daniel Ismail. My matric number is 208078. Along with me, I introduce you two of my friends which in my group. Aiman Amirul Faris bin Kamisan 208224 and Muhammad Hazim bin Abdul Rahman 208339. So we are going to we're going to present our topic, which is moment of inertia of the beam calculator. Okay, what is the area moment of inertia? Area moment of inertia, or known as the moment of inertia, for an area is used to predict deflection, bending, and stress in beams. For your information, the larger the moment of inertia, the less the beam will bend. And in the structural engineering, the area moment of inertia of a beam is important because it used in the calculation of the beam deflection and the calculation of the stress which caused by the moment applied to the beam. And there are four types of beam that have been used in our project, which are rectangular beam, I-beam, T-beam, and lastly L-beam. Okay, for the rectangular beam are more often used in the office or commercial building, while the I-beam have a variety of important use in the structural steel construction industry, and they are often used as critical support truss or as the main framework in the buildings. Okay, moving to the next point, for the T-beam. T-beams are more often used for more heavy duty or larger span such as bridge. And lastly, for the L-beam. L-beams have minimal structural depth, so the L-shaped beam are more stable, and therefore they are commonly used to anchor a flooring system of a building foundation. Next, Faris will continue the presentation.
Okay, now I will continue by presenting the project background. Okay, a beam is a structural element that is designed to resist loads that are applied laterally to the axis of the beam. Bending is the primary means of deflection for it. Reaction forces are generated at the beam's support points by the loads applied to it. All of the forces operating on the beam result in shear force and bending moment within the beam, which causes internal stress, strains, and deflection. The second moment of area of a beam is an important feature in structural engineering that is used to calculate the deflection of the beam as well as the stress induced by a moment applied to it. A considerable portion of the cross-sectional area of beam is situated at the largest possible distance from the cross-central section in order to maximize the second moment of area. The planar second moment of area reveals a beam's resistance to bending as a function of its shape in the presence of an applied moment, force, or distributed load perpendicular to its neutral axis. Okay, in our project, we are going to calculate using MATLAB the second moment of area acting on four types of beam: I-beam, H-beam, L-beam, and rectangular beam. By using this program, engineers can determine the center of mass of beam section. This program is also useful for beam analysis when the moment of inertia is required for calculation such as shear or bending stress and deflection. To calculate the centroid, the beam has to be split into appropriate segment. After this, the area and centroid of each segment need to be considered to find the centroid of the entire section. So for our program, we use three types of formula. The first formula is the formula to calculate the vertical Y centroid of a multi-segment shape. Next, we use the formula to calculate the moment of inertia of each of the segment. And lastly, we use the formula to calculate the total moment of inertia of the section. Now, I will pass the presentation to Muhammad Azim. Thank you.
Thank you, Farish. My name is Muhammad Hazim bin Abdul Rahman and my matrix number is 208339. So now I am going to continue the presentation by explaining about the program development. For the program development, first of all, we are going to discuss about the development of moment of inertia calculator. In the development of the calculator, a graphical user interface GUI in MATLAB had been used in order to build the moment of inertia calculator. As shown in the figure is where the progress began. Components that had been used included edit text, static text, push button, pop-up menu, access and also panel. The pop-up menu was used to show 4 options of beam types, which is rectangular beam, I-beam, T-beam, and also L-beam. The access component was used to show the image of the beam that had been selected by the user. In the Insert Dimensions panel, the user will be asked to insert the dimension of the selected beam, which can be referred to the image depicted in the calculator, which is in the Access panel. The answer of the moment of inertia (MOI) and also the centroid of the selected beam will be shown in the answers panel in the top right corner, in the bottom right corner. After selecting and arranging all of the components, we will then change those strings name and text name based on their function before starting to program the calculator. After that, we proceed to program the calculator. We started by inserting a few lines of commands to allow the access component to show the beam's image that the user desired. We used switch case operations to read the image file based on what the user chose in the pop-up menu. Note that the image will only be read by the programs if the file of the image is in the same folder as the code file is. Then we move to the major steps in building this calculator. We now started to program to allow the execution of push button. In this process, firstly, we had converted all of the desired strings in the GUI figure to number to allow the programs to read them. All of them can now be used in the formula to find the centroid and the moment of inertia that had been written in lines of commands. The centroid and the moment of inertia value were then converted back from number to string to allow the value to be shown in the answers panel. Now we can already run the program and the calculator is ready to be used. Now we are looking for a few relationships between the area and centroid, the area and moment of inertia, and the centroid and moment of inertia. Note that to find these relationships, we will use a rectangular beam as it will apply the same method for the other beams, which is I-beam, T-beam, and also L-beam. This is because those beams are calculated by adding the segments of the beam, which each of them is rectangular shape. So first, we are going to find the relationship between area and centroid. To find this relationship, we used the range of 1 to 10, which is spacing of 0.01 for the height and width of the beam. Then we started to find the area and centroid using the selected range. Finally, we plotted the relationship with the area set to be the x-axis and the centroid to be the y-axis. The line width of this plot is 2 and colored blue. X-axis was labeled as area, which in unit mm squared, while the y-axis was labeled as centroid in mm, with both of the axes having a font size of 17. This plot was named relationship between area and centroid for rectangular beam, and the grid is enabled in the plot. Next, we are going to find the relationship between area and moment of inertia. To find this relationship, we will use the same range as a previous relationship, which is from 1 to 10 with spacing of 0.01 for the height and width of the beam. Then we started to find the area and moment of inertia using the selected range. Finally, we plotted the relationship with the area set to be x-axis and the moment of inertia to be the y-axis. The line width of this plot is 2 and colored as red. X-axis was labeled as area unit millimeter squared, while the y-axis was labeled as moment of inertia unit millimeter to the power of 4, with both of the axes having a font size of 17. This plot was named relationship between area and moment of inertia for rectangular beam, and the grid was enabled in the plot. And finally, we are going to find the relationship between centroid and moment of inertia for rectangular beam. To find this relationship, again we use the same range, which is from 1 to 10 with spacing of 0.01 for the height and width of the beam. Then we started to find the centroid and moment of inertia using the selected range. Finally, we plotted the relationship with the centroid to be the x-axis and the moment of inertia to be the y-axis. The line width of this plot is 2 and colored as green. X-axis was labeled as centroid in millimeter, while the y-axis was labeled as moment of inertia in millimeter to the power of 4, with both of the axes having a font size of 17. This plot was named as relationship between centroid and moment of inertia for a rectangular beam, and the grid was enabled in the plot. Okay, so now we are looking for the results. As depicted in the figure is the moment of inertia calculator. At first, the users need to choose the beam type, which is rectangular beam, I-beam, T-beam, or L-beam. Next, they will be asked to insert the dimensions of the selected beam, which can be referred to the figure shown in the calculator. After that, they can proceed to push the calculate button, and the results of the centroid and moment of inertia will be shown up in the bottom right of the calculator. Next, for the relationships between area and centroid for rectangular beam, we can conclude that when the area increases, the centroid will also increase. The line is increasing and concave downward. For the relationship between area and moment of inertia for rectangular beam, we can conclude that when the area increases, the moment of inertia will also increase, while the line is increasing and concave upward. Lastly, for the plot of the relationship between centroid and moment of inertia for a rectangular beam, we can conclude that when the centroid is increasing, the moment of inertia will also increase, and the line is increasing and concave upward.
Thank you, Hazim. Now I will continue by presenting the other section. Okay, the area of an efficient deflection beam is formed in such a way that the regions are concentrated as far away from the beam's center as practicable. Taking the moment of areas around the center is an expression to check how well this has been accomplished. The moment of inertia is the term for this. As a result, the lesser the deflection, the further the regions are from the centroid. Now I will pass the presentation to Ahmad Daniel. Thank you.
As for conclusion, the moment of inertia equation are extremely useful for the fast and accurate calculation. In the equation, the area moment of inertia is represented by I, and it is said a beam tends to change its shapes when it is loaded. Hence, the moment of inertia was used to measure the efficiency of a shape to resist bending caused by the loading. And the moment of inertia provide insight into a beam resistant to the bending of a beam due to the applied moment or force that perpendicular to its neutral axis. Besides, the moment of inertia also provide insight into a beam resistant to its torsional deflection, which is due to an applied moment parallel to its cross section. I think that's all from us. Thank you.